So exam one is going to have a take-home part and an in-class part. The take-home part, that will open on Canvas at 11 a.m. today, right? So when our class is finished, the Canvas assignment will open and you'll be able to go in and see the questions. I made the due date for this, it's actually Tuesday, so you have a little bit of extra time. Tuesday, I believe, is the 23rd at 3 p.m. Okay, so the questions are on Canvas. You will write up your solutions, pencil and paper, and submit your written work to me. And the in-class portion will be on Monday, February 22nd. Okay. I haven't actually posted this yet, but I will soon, this afternoon. A list of essential definitions and theorems. Okay, and this is going to be particularly important because the test is going to ask some definitions. Okay, so you probably know already some of the things that are going to be on there. For example, what do you think I'm going to put on here as lists of essential definitions? Let's focus on the definitions for right now.
And should that be a pretty good like study guide type to like what we should look over for the in-person part?
Yeah, yeah. So anything I said that was something like, I would expect a student coming out of this course to be able to do this or to know that. There were a few that I mentioned. Can you remember any of those?
Prove the square root of 2 is irrational.
Okay, right. That's a proof.
Oh yeah, you
Yeah. Which is that type of proof is certainly something we should know. I was thinking more of like definitions.
Bounded sequence.
Okay, right. What is the definition of a sequence being bounded? Now, one of the things I might point out is that, whoops, I turned off the video. I wanted to switch. Okay. One of the things I might mention is some folks said, well, it's bounded if it has a sup. Okay, but the supremum of a set applies to the set being bounded. So in a way, being bounded is like more fundamental than having a supremum. Okay, so the definition of a bounded sequence. What else? Something that we have to use in important proofs.
Epsilon minus n proofs.
Okay, so epsilon big N proofs. So now what definition are we using there?
think it's the limit definition.
Right, the definition of what it means for a sequence to converge. Okay, so you've got to know that definition because we use that in the proof. Okay, so you've got to know the precise statement of that definition. Okay. What does it mean for two sets to be equivalent?
They have the same cardinality.
Okay, same cardinality. And how would we prove that the two sets have the same cardinality?
There's a one-to-one onto function between them.
Okay, right. So one-to-one onto function. So now we're kind of getting into this almost like a little chain of definitions here. Okay, two sets have the same cardinality if we can produce a one-to-one and onto function f with one set as the domain and the other set as the range. Okay, well, what does it mean for a function to be one-to-one and onto?
One-to-one is like one thing in the domain produces one thing in the range.
Okay, this is something we got to be careful about here because that's the definition of a function. Every element in the domain is paired up with exactly one element in the range. So that's a function, not a one-to-one function.
I guess like the 2-to-2 thing you said were like,
Yeah, okay. So if you take two different things in the domain, then you are guaranteed to get two different things in the range. Okay, that's one-to-one. And the definition kind of tells us how to prove a function is one-to-one. We start with two things in the range that are equal, and then we show that the two things in the domain that created them had to be equal. How about onto? How do I prove something is onto? What does it mean for something to be onto?
There's no holes, so like the range is from negative infinity to infinity.
Okay, right. If we're talking about a set from the real numbers to the real numbers, if we're talking about a function on the set of real numbers, that would mean that everything in the range is covered. And we can kind of extend that idea a little bit to just more general sets. If I take an element in the range, an element in my sort of target space, I have to be able to produce something in the domain that maps over to that element in the range. Okay, so there will be questions on the test where I simply ask you to state a definition. Okay, and in those cases, of course, I'm looking for the full, precise definition. So I'll make you up that list. And the essential theorems will be things that we can cite when we are doing some proofs. Okay. So, for example, oh gosh, where was one that we had to use this? I mean, we have to use them a lot, so kind of a good idea to know them. But there was one we were just talking about in office hours here.
BWT.
Okay, yeah, right. The Bolzano-Weierstrass theorem over here in. Let me switch to the document camera. We were talking about citing this when we were doing, or we were talking about this problem here. It says, give an example of each of the following or argue that a request is impossible. Okay, so a sequence that has a subsequence that is bounded but contains no subsequence that converges. Okay, well, I think we decided that if this were true, it would contradict the Bolzano-Weierstrass theorem. Because we have a subsequence that is bounded, Well, every subsequence is a sequence. So we could apply the Bolzano-Weierstrass theorem to produce a convergent subsequence of this. But that, of course, would be a subsequence of this over here, the original sequence. So we would be able to produce a convergent subsequence from the Bolzano-Weierstrass theorem. Okay, so that list of essential theorems will be things that we can cite to help us prove other things. So we had a few of those. Help me with those. Oh, no, turned it off again. So help me with those. The Bolzano-Weierstrass theorem would be one of them.
The monotone convergence theorem.
Okay, right, the monotone convergence theorem. Okay, and we had that kind of little chain of reasoning there. So the monotone convergence theorem is what we use. Actually, no, I guess not. To prove the Bolzano-Weierstrass theorem, we use the nested interval property. But the monotone convergence theorem is like a special case of the Bolzano-Weierstrass theorem almost. Okay, so what's another one? So we got Bolzano-Weierstrass, monotone convergence theorem. What are some other big ones?
Axiom of completeness.
Okay, the axiom of completeness is sort of at the base of all this, kind of the most fundamental thing is the axiom of completeness. Now that's something we do have to use a lot. It's not really a theorem though. It's just something. Just a quick question. So do we understand the difference between an axiom and a theorem? Like, why do they have two different words? Why isn't it called the theorem of completeness? Why is it called the axiom of completeness?
An axiom is just like understood to be true.
Right. An axiom is like a premise that we are accepting without proving it. So let me see here. Let me go switch to the document camera. So we have the axiom of completeness. And in this little chain of reasoning, we had, and I think this is something I put on the board, the board last time, but the axiom of completeness eventually implies the Bolzano-Weierstrass theorem, which implies something else that we talked about last time. There's a little middle part in here. So what did we use to establish the Bolzano-Weierstrass theorem again?
The MCT.
Actually, I don't think that comes up. It's actually, the MCT is like a little separate thing down here. You need the axiom of completeness to establish the monotone convergence theorem, but we didn't actually use monotone convergence to get to Bolzano-Weierstrass.
The nested interval property.
Right, it was the nested interval property. So axiom of completeness gives us the nested interval property, which gives us the Bolzano-Weierstrass theorem. And then we used the Bolzano-Weierstrass theorem last class to prove something else.
The Koshi Criterion.
Right, the Koshi Criterion. So tell me a little bit about the Koshi Criteria. We'll do a quick review. Oh, and I'm sure you will already know this, but this little chart here is a pretty good indication of the essential theorems. Of course, we know this is not a theorem, but all of these are. Okay, there's one more essential theorem I can think of, but we didn't really use the axiom of completeness necessarily to get there. There's one more theorem that we use a lot.
Is that the Archimedean?
Okay, the Archimedean property, kind of. We do use that to, especially when we were proving that like sequences go to zero or things like that. That came up a lot. I was actually thinking of the algebraic limit theorem with those four parts. So it basically showed us that we could do the manipulations that we would expect to do with these sequences. So that's something else I would consider an essential theorem. But what's a Koshi sequence?
It's a convergence sequence.
That's true. If we have a Koshi sequence, then it converges. So this will be another one of our kind of essential definitions. A Koshi sequence if I say a sequence is Koshi, we do have a theorem that says my sequence would converge.
For any greater than
Okay.
0, they're
Okay, for all epsilon greater than 0, there exists capital N in the natural numbers.
such that n and m are greater than n.
Implies what?
A sub n minus a sub m
Okay,
is less than or equal to epsilon.
right, okay. So that's the definition of a Cauchy sequence. I kind of wrote that out in our mathematical shorthand there. For all epsilon greater than 0, there exists n. Yeah.
Dr. Mack, I feel like I'm pretty sloppy with greater than and greater than or equal to.
Okay.
So does that matter on the epsilon part on the bottom?
On the epsilon, I think we really need that to be strictly less than.
Okay.
I think you're allowed to play around up here. I guess you could argue that we can get away with having less than or equal to here if it's for all epsilon greater than 0.
So is the absolute values of a sub n minus a sub n less than epsilon, is that saying that like any two terms, like the distance is less than epsilon?
As long as you have gone far enough out in the sequence.
Okay.
So basically it's saying that the terms of the sequence get closer and closer to each other if we go far enough out. So the kind of advantage that the Cauchy condition for convergence has is that you don't need to know the limit of the sequence. If you're going to prove a sequence converges from the definition, you have to know the target that it's converging to. sometimes you can't always make a guess about that. But the Koshi condition just lets us look at the individual terms, and if we can see that the difference between any two terms out in the sequence is getting small, then the sequence must converge. We have a theorem about that.
Do they have to be consecutive terms?
Actually, no, they don't. In fact, you have to show what we're doing is we're showing that. So let's say, for example, n was 1,000 for this particular epsilon. We're given a particular epsilon, we find that n is 1,000. Then it's true that term number 1,000 minus term number 1,001, that has to be less than epsilon. But term number 1,000 minus term number 1,000,000 also has to be less than epsilon. As long as I'm past term number 1,000, or at least at term number 1,000, any two terms from there on out should be within epsilon of each other.
Okay, thank you.
Sure.
I got a question.
Yeah, go ahead.
Since the a sub n minus a sub m is less than epsilon, couldn't you, and it's for any epsilon, couldn't you just say it's less than any epsilon times a constant? You know how we have to do like epsilon over 2 for a bunch of things?
Yeah.
Couldn't you just say, since epsilon can be any number greater than 0, it has to be less than epsilon times any constant?
Yeah, that would, I mean, that's kind of in here, right? Because it's for all epsilon greater than 0.
Yeah, I just like whenever we do the scratch work, can
Yeah.
you and say straight away it's less than epsilon over 2?
Right. If you have something that is Koshi, then you know you have this, and then you can replace epsilon with basically anything. You can find an n that makes it work.
Okay.
Even if it's epsilon over 2 or epsilon over 3 or whatever. Okay. So let's just do a couple little practice proofs and warm-ups and things like that. Okay. Tell you what, if you've got your book, come with me to page 55. Okay, we're in section 2.3 here. So it reads this: a typical task in analysis. Okay, so analysis is the branch of mathematics that deals with infinite processes. So calculus belongs to analysis. Okay, so a typical task in analysis is to decipher whether a property possessed by every term in a sequence is inherited by the limit of the sequence. Okay, so that's kind of the a recurring theme. So for example, if I had a sequence of functions, let's say, and every term in the sequence was differentiable. So let's say I had a sequence of functions where every term had a derivative. And let's suppose the sequence of functions converges to some function. If all the terms in my sequence are differentiable, does that necessarily mean that the limit is differentiable? Okay, so in other words, we're talking about what are the properties that survive the limit process. Okay, so here's we'll deal with sequences of functions a little bit later in the course. But this is about sequences of constants. Okay, so let's look at this here. If every term in my sequence is an upper bound for the set B, then the limit is also an upper bound for the set B. Okay, so sometimes I like to phrase a question this way. Prove or find a counter example. Okay. So, firstly, when I phrase a question like this, I don't mean you can do one or the other, okay? Either the statement is true or it's not. We have to decide which it is, okay? We have to make that decision first. If we are thinking that the statement is true, then we'll need to prove it. If we're thinking the statement is not true, then we will need to produce a counter example.
I think it's true.
Okay, so you're thinking, say again?
I also think it's true.
Okay, you also think it's true. Okay, so we're thinking that it is true. Okay, now we do need a definition here. Of course, we need to know precisely what they mean by upper bound, and that's something we probably remember. The definition is on page 15. Okay. So, looking right here, right, an upper bound for the set A is having this property. So you're allowed to have equality. It's greater than or equal to. And I think that kind of saved us, because if it was just greater than, I think we might have a bit of an issue. Okay, so we're thinking that it's true. So then we should try to work on a proof. And this is something I might try to prove by contradiction. Okay, now how does this work again? A proof by contradiction?
You assume the negation is true.
Okay, so we're starting with the negation. Now, the negation of what part? Are we going to assume that A sub n is not an upper bound for B for all n?
No, it's that is true, and A is not an upper bound.
Okay, right. So we're keeping the premise, but we're supposing that the conclusion here is false. So what we're going to do is we're going to suppose A is not an upper bound for the set B. All right, now what does that mean? A is not an upper bound.
There exists a term in B that's greater than.
Right. Okay, so Thus, there exists, let's call it little b in B, such that let me write it the other way. A is in fact less than B. Okay, now what we're kind of shooting for here when we're doing this proof by contradiction is we want to produce terms in the sequence that are not upper bounds anymore for the set B. Okay, because remember, we're keeping the premise. We're trying to have the premise and the opposite of the conclusion. So we're trying to have A not be an upper bound while all the A sub n's are. And we want to break that. So the way to break it, I think, is we should try to show that now that we've got this, let's show or try to produce terms in the sequence that are not upper bounds. Okay, so how are we going to do that? What's our idea? Let me throw out a little scratch work here. A couple of things I know. The A sub n's converge to A. So the A sub n's can be made arbitrarily close to A. How close? Well, since A is less than B, maybe I can do something about the distance between A and this element B. In fact, I might do something like this. I might say let epsilon equal B minus A over 2. Something like that. So because A sub n converges to A, we know there exists capital N, a natural number, so that this inequality holds. Okay, and let me get a little piece of scratch paper here. All right, so let's think about like a number line here. So this is my set B over here. So we were saying that the limit A is like there, right? And that was not an upper bound. So we produced an element little b in the set that was bigger than A. All right. Now notice what I did there. I did B minus A. So that's this distance cut in half. Okay, so this was my epsilon. Maybe I shouldn't have drawn it that tiny. Okay, but I guess with my camera I can just zoom in. So there's my epsilon, the distance between A and B. Now what we've just shown is that since A sub n converges, all the terms in the tail are within epsilon of A. Okay, so help me put a bow on this. Help me finish off the proof.
Plug the epsilon in.
Okay, right, so we're going to use that epsilon. Okay, so oops, I think I messed up my kind of alignment there. Okay, so we've got that epsilon right there. Maybe I'll even say B minus A over 2. Now, kind of remember that we've got kind of the conclusion that we know we're going for. I want to be able to say thus A sub n is less than B for n greater than or equal to capital N. A contradiction. Okay, now I can't quite say that yet because I need to fill in, I need to establish why this is true. Right, so what can I do? Help me out with some inequalities here.
Can you take the absolute values off the A sub n minus A?
I'm not quite sure I can do that. I mean, we might be able to do some stuff with.
Can we add a B and subtract a B?
Okay, so right, so we're gonna have to work a B in here somehow, right? So what we want to say something about the A sub n's and the B's, or not the B's, this one particular B. Okay, so we need to bring B into the picture somehow. All right. Now, I guess one of the things we can do is if I ever have a B minus A, that's positive. I know I can take that to be positive. Okay, so maybe we could throw that in there in the middle. Okay, so epsilon. So we're working on this here. We got A sub n minus B plus B minus A. And we know we can make this thing arbitrarily small.
You can say that's less than B minus A over 2, can't you? Because epsilon equals.
This?
Yes. Is less
Yeah. So this is less than B minus A over 2.
Can we use the triangle inequality?
Okay, we can probably apply the triangle inequality here. So we can do something like this. So we could replace this with a sub n. Now a sub n minus b plus b minus a. Okay. And we know that this is actually less than this. And this whole expression can be made less than that. So we're thinking about eventually relating the a sub n's and the b's. And we kind of want this. And remember our picture here, right? So the a sub n's have to get within epsilon of a, which is right here. And the way we chose this epsilon was that b exceeded a plus epsilon. Okay, so maybe that's something we could work in here. Okay, so this is kind of becoming scratch work right here, but that's okay. Okay, we can add it to we can add the appropriate parts to our full write-up. Okay, so the a sub n's are within epsilon of a. So let's see if we can do something with like, so b is definitely greater than a plus b minus a over 2. Okay, because this was not the full distance, it was half the distance. Which is greater than a plus epsilon. Okay, maybe we could somehow work the epsilon in here and kind of work some a sub n's in here. Do a couple cases or something like that. Okay, so something like basically, because we've got this right here, epsilon is bigger than the distance from an and a. Okay. Now, the thing is, we've got this inequality to, or sorry, we've got this absolute value to worry about here. Okay, now, if an is bigger than A, then this expression, A sub n minus A, would be positive.
Then you could drop the absolute.
Then we could drop the absolute value. Okay, so let's look at a couple of cases. AN bigger than A, that implies AN minus A is bigger than 0, which implies absolute value AN minus A is equal to AN minus A. Thus, B is greater than, and I'm just going to write what I had before, A plus B minus A over 2, which is greater than A plus epsilon, which is greater than A plus absolute AN minus A, which is equal to A plus AN minus A, which is equal to AN. Okay, so we have this whole chain of inequalities here, getting B greater than A sub n. Now this is the case where A sub n is greater than A. What's the other case we should look at?
A sub n is less than A.
Right, the other way, the other inequality. In fact, I'll deal with less than or equal to here. Now here I had to kind of do a little bit of gymnastics, getting things set up correctly to do this, to eventually get that B is greater than A sub n. This one is super easy. What's the relationship between A and little b?
Little a is less than little b.
Right, little a is less than little b. So since a is less than b, this implies a sub n less than or equal to a less than b, and we've got the inequality. Either way, a sub n is less than b for all little n greater than or equal to capital N, a contradiction. Okay. So we got our proof there, and we really needed to use.
Dr. Mack,
Go ahead.
can I go back and get that, what you just wrote?
Okay, yeah, it was the conclusion that I had on the other page.
I got it.
Okay. So a couple of things we had to use, right? We had to use what we know about the definition of convergent sequence, okay? If we're saying that the a sub n converge to a, we're saying this holds for all epsilon. Now here we used a particular instance of it because we're working a proof by contradiction with this b minus a over 2 business here. Okay, that was to just get us closer to a than we were to little b, so that we could be sure to be less than. Got some scratch calculations over here that eventually led us to this. Okay. So that's a typical theme, as I mentioned, in analysis. You got a sequence. Every term in the sequence has a certain property. Is that property preserved when you go to the limit? So in a way, analysis is like the study of what survives the limit process. Okay, so it might not hurt to look at 2.3.12, exercise 2.3.12. There are two more parts on page 56. So it might not hurt to look over those and think about those, okay?
Is this
So-
kind of like types of questions we should prepare for the in-person part of
I
our?
probably wouldn't put one that had you do a proof like this on the in-person part, because when you're doing a proof, you sometimes have like a full, like when I did this proof, I kind of had like a false, I kind of had this little false start here. It's not really a false start, but this isn't the way my write-up ended up looking. I'm like, okay, well, maybe we can try this. We know we need to get the B in here. Let's subtract and add the B. So I eventually did use this, but because of that type of thing that happens in proofwriting, I probably won't ask you to write a proof like this on the test. But not every part of 2.3.12 is going to require a proof. Okay, so think about that. Okay, so the exam should open up at 11, the take-home portion. So I would recommend getting started on that this afternoon. You do have till Tuesday, but don't wait till Tuesday to get started, all right?
Sounds good.
Okay, I'm gonna go ahead and stop the recording.